Welcome back to the Advanced Microcontroller series. In this session, we are learning about polling. In the previous session, we discussed about the disadvantages of polling, that is bad response and loss of event. But in today's session, we are discussing about another disadvantage, that is inefficient power management. Let's show with example. So if it is polling, is it possible to put the microcontroller to sleep mode? No, right? It is not possible. Do you think external interrupt have the ability to wake the system up from the sleep mode? Okay, let's check this in data sheet. So this is the data sheet. So here you can see the INT interrupt can wake up the processor from sleep if bit INT was set prior to going into sleep. So when INTE was set, means when INTE equals to 1. Yes, it is possible, right? The external interrupt have the ability to wake the system up from the sleep mode. Okay, now let's open the code, file, open project, power management. So here source file main.c. So here init config. So here you can see count equals to 5, long I, character, char, key. So init config. So control will come to the main function. So here you can see while of 1 if count not equals to 0. So initially we declared count equals to 5. So count not equals to 0. Now 5 not equals to 0, condition true. 4 not equals to 0, condition true. Then again 3 not equals to 0, condition true. 2 not equals to 0, condition true. Again 1 not equals to condition true. Then 0 not equals to condition 0. Is this condition true? No. Here condition false. 0 not equals to 0. Now what will happen? Controller will come out of the loop. So how did you call the sleep function? So here we need to use the sleep function, right? So how did you call the sleep function? So sleep, like this. So need to pass an argument. Sorry, like this. So which compiler used to execute this like this sleep? GCC, but we are using XE8. So here it is different, right? Go to the compiler guide. So search XE8 compiler guide for PIC microcontroller. Then you will get this one. So then search sleep. So here you will get sleep macro. A sleep macro that puts the device into sleep mode. So here you can see xe.h. So void sleep of void. See here sleep function. This is what sleep macro. But in the data sheet here you can see INTE was set prior to going into sleep. So So what we need to do in the code, we need to mention int equals to 1. So here you can see, before make use sleep function, int equals to 1, and here we call it external init function first, not init config function, isn't it? Not this one, we call it this one first. So when count equals to 5, it will check the condition, count not equals to 5 not equals to 0, then 4, 3, 2, 1, then it will come out of the loop. So okay, let's build the code and check it in PICSimLab Simulator. Build is successful. Go to the PICSimLab Simulator, file, load hexa file. So this one, power management. So here you can see on, off, on, off, on 5 times, right? So 5 times it's toggling on, off, on, done. So now we need to wake up by pressing the switch again. So again press, see LED 1 on again, see 1 on, off, off, sorry, off, on, off 5 times, isn't it? So here LED 1 toggles once, then LED 2 5 times. Again here you can check on, off, on. See, that's all about the polling. And next we will discussing about the microcontroller interfaces with timers. Okay, let's discuss about the another peripheral, that is timer. And here is the agenda, introduction, example. So what is timer? So this is another peripheral. Okay, this is a peripheral which is used to capture or measure the running time. Once it is started, it should never stop. When talking about time, we have to aware of this concept. All the microcontroller is having built-in peripheral, that is timer. So here we having some of the concept: resolution, tick, quantum, scaling, modes, counter, PWM or pulse generator, PW or PP measurement, etc. So what is resolution? So before that, timer use it for what? To measure running time, isn't it? So it start measuring like 1 second, 2 second, 3 second, keep measuring. To store this time which is being counted by the timer, we need register. So register we need. So I am naming this register, that is timer register, as TMR. So here this is what? TMR. I am naming this register as TMR. Whatever time measured by the timer is stored in this register. So what is resolution? Width of the timer register. This can be either 8-bit or 16-bit. Let's assume timer register is 8-bit. So how much maximum value you can store inside this? So how to find? So 8-bit, right? So 2 to the power, 2 to the power 8 minus 1. That is the answer. That is what? 255. So based on the bit we can store register data. So if it is 16 bit, then so 16 bit, right? 2 to the power 16 minus 1. 65535. So 0 to 65535. Now here I am assuming 8 bit. So 1, 2, 3 up to 255. So how much is the changes happen here? 0 to 1, 1. Sorry, it is 2, okay. How much is the changes happen here? 0 to 1, 1. Then 1 to 2. How much? Again 1. Similarly 2 to 3, 1. So this change is referred as tick. Okay. After every tick, change happen in timer register. 0 to 255. So how many ticks possible? 255 ticks, isn't it? Okay. Our second concept is tick. So ticks in timer. So or 8 bit is, for 8 bit how many ticks are there? 255. So tick can either up count or down count. So here you can see either up count or down count. So what is happening? So here you can see in the previous example 0 to 1, 1 to 2. So it is up counting here. So once timer is started, it start ticking. So how much duration it takes to happen change from 0 to 1 or 1 to 2? That is called quantum. So quantum is what? Tick duration. So quantum is nothing but tick duration. So in case of PIC microcontroller, quantum directly depend on system clock setting. The tick is based on instruction cycle. After every instruction cycle, tick happens. So how much time does a instruction cycle tick? Sorry. How do you find the time? So we know time is inversely proportional to frequency. So time is equals to 1 over frequency, isn't it? So, but in our microcontroller, it takes 4 pulses to get one instruction executed. So here time is equals to 4 into 1 over 1 divided by frequency. So here I am adding bracket. So 1 over frequency. So now frequency is nothing but oscillating frequency, isn't it? So how much is the oscillating frequency? 20 megahertz. So time is equals to 4 into 1 by 20 mega means how much? 10 to the power 6. So now we need to solve this. So that is equals to 0.2 microsecond. So now we need to convert this with respect to nanosecond. So time equals to t equals to 200 nanosecond. So after 200 nanosecond, one tick happens from 0 to 1. Then again after 200 nanosecond, 1 to 2. So what is the total time to complete 255 ticks? For one tick takes 200 nanosecond. So for 255 ticks take how much? 255 into 200 nano, that is equals to 51,000 nanosecond. So we can write it as 51 microsecond. So you can write it as 51 microsecond. So it uses 51 microsecond. So after 255 ticks, can I increase 255 to 256? No, not possible. So assume there is a main function. So here I am going to write one main function. So here timer on. So while of 1, so here we having semicolon, then close the bracket, then close the flower bracket. So up to how much time the timer count? It counts till 51 microsecond. It counts up to 51. So it cannot go beyond this. Do you think this happen in real time scenario? Yes, it happens. So it runs after 51 microsecond. So how that happens? After 255 it will roll back to 0. Before roll back, it generate INT and it will tell I am full. Please read the value. So whenever INT generate, control go to the ISR. So meanwhile, what is the timer do? Again it start counting 0 to 1, 1 to 2. So after how many tick INT get generated? It generated after 256 tick. So what is the total time to takes to get the INT generated? So 256 into 2 nanosecond. That is how much? 51.2 nanosecond. Sorry, not nanosecond, it is microsecond. So after 51.2 microsecond there is a INT get generated. So now I am considering one more function. So main, open flower bracket, while of 1, so here I1, I2, then I3, then close. So here what will happen? Control is busy executing this. So after 255 it will go to 0. Interrupt is generated. Control goes to here. Control goes to here, ISR. Control goes to here. Then control comes back to the place where it was interrupted. Still executed I1 again after 51.2 microsecond. Again it started counting. Again control goes to the ISR. So to avoid this, we need to add some delay. So that is about the quantum. And next is the scaling. So these concepts we'll discuss in the next session. That's all about the today's session. Thank you all.